Hello and welcome. In this notebook, we continue Docker with Part 2. First, we cover Docker Compose for multi-service apps. We learn why Compose is better than long Docker run commands, how to write a minimal Docker Compose.yml, understand its structure, run commands like up, down, and logs, and use .env files for configuration. Next, Debugging and Maintenance teaches us how to check logs, monitor containers with stats and top, set restart policies, and clean up unused resources with Docker System Prune. Then, in the real-world project, we Dockerize a web app, add a database with Compose, use volumes for persistence, and run everything with one command. Finally, in deployment basics, we push and pull images via Docker Hub, create smaller production-ready images using multi-stage builds, and follow security best practices like running as non-root and using Alpine images. This part shows how to build, run, and deploy containers like in real-world projects. Why Docker Compose? So far, we have been using the docker run command to start containers. That works fine for 1 or 2 containers, but in real projects, you often need many containers working together. For example, a web app might need a web server, a database, a caching service, and more. Typing long docker run commands for each container with volumes, ports, and networks quickly becomes messy. This is where Docker Compose comes in. Compose lets you describe your entire multi-container setup in a single file called docker-compose.yml. Instead of running many commands, you just run docker-compose up and everything starts together. It also makes projects easier to share. If someone else wants to run your app, all they need is your Compose file, and they can start the whole system with one command. In short, Docker Compose makes multi-container apps simple, repeatable, and professional. Minimal Docker Compose.yml. Now let's see Docker Compose in action with a simple example, a web server and a database. With Docker Compose, you describe everything in one file called docker-compose.yml. This file is written in YAML format, which uses indentation with spaces, not tabs. Inside the file, you list all your services, for example, one service for a web app and another service for a database. Each service can define its image, ports, volumes, and the network it belongs to. Once the file is ready, you don't need to run multiple commands. You just type docker-compose up, and all containers start together already connected to the same network. This makes running multi-container projects much easier. Here's a minimal docker-compose.yml file. At the top, we write version :3.9, which tells Docker which Compose file format we are using. Next, we define services. The first service is called Web. It uses the Nginx image, and we map port 880 on the host to port 80 inside the container. This means we can access the web server at localhost :880. The second service is called DB. It uses the Postgres image, which is a database. We set one environment variable, Postgres_password equals secret. That sets the database password. That's it, just 2 services in one file. To run this setup, we save the file as docker-compose.yml. Then, in the same folder, we run the command docker-compose up. Docker will start both the web server and the database, and automatically create a network so they can talk to each other. This is the simplest form of Docker Compose, but it already shows its power. Anatomy of Docker Compose, YML. To really understand Docker Compose, let's break down the structure of the docker-compose.yml file. The file starts with a version line. This tells Docker which Compose format we are using. Most modern examples use version 3. Next comes the services section. This is where you define each container you want to run. Every service has a name, like web or DB. Under that name, You write settings for that container. Common settings include image, which tells Docker which base image to use, ports, to map ports from your computer to the container, environment, to pass variables like passwords or configuration, volumes, to attach persistent storage. One important note, YAML is very sensitive to spaces. Use spaces for indentation, never tabs. Each level is indented by 2 spaces. With this structure, you can read and write compose files, even if they are more complex. In this example, we start with version 3.9. Next, the services block begins. The first service is web. It uses the Nginx image. It maps port 8080 on the host to port 80 inside the container, so you can visit localhost 8080 in your browser. It has a volume line, ./html:/usr/share/nginx/html. This means the HTML folder on your computer is shared into the container, where Nginx expects website files. The second service is DB, which uses the Postgres image. Under environment, we set 3 variables: Postgres_user equals admin, Postgres_password equals secret, and Postgres_db equals mydb. These set up the database user, password, and default database. Then we add a volume, db_data:/var/lib/postgresql/data. This stores the database files outside the container so they don't get lost. Finally, at the bottom of the file, we define volumes. Here we declare db_data, which is the named volume we used in the database service. This example shows almost all the common parts of a compose file: version, services, image, ports, environment, and volumes. Docker compose commands. Once you have a docker-compose.yml file, you control everything with a few simple commands. First, use docker-compose up to start all services. This will read the file, create the network, start the containers, and connect them. By default, it shows logs directly in your terminal. Second, use docker-compose down to stop and clean up. This removes the containers, the network, and by default, any volumes created for that project. It's like shutting down the whole system with one command. Third, use docker-compose logs to check the output of your services. This is very useful because you can see logs from multiple containers in one place. You can even add options like -f for follow to see logs updating live. And remember, you always run these commands in the same folder where your docker-compose.yml file is located. With just these 3 commands, up, down, and logs, you can manage multi-container apps like a pro. Here's how we use these commands in practice. First, type docker-compose up to start everything. If you want the containers to run in the background, add the option -d for detached mode. When you're done, type docker-compose down. That will stop all the containers, remove them, and also remove the network and volumes created for the project. To see what your services are doing, type docker-compose logs. This shows logs from all containers at once. If you want to watch logs in real time, add -f at the end. Using .env with Docker Compose. When building real projects, you don't want to hard-code passwords, usernames, or other configuration directly inside your docker-compose.yml file. Instead, Docker Compose supports the use of an environment file, usually called .env. You create a file named .env in the same folder as your compose file. Inside, you define key equals value pairs, such as database usernames and passwords. Compose automatically loads this file. In your docker-compose.yml, you can then reference the variables using the $ and curly braces syntax. For example, $curly brace, Postgres_user, curly brace. This makes your setup cleaner, more secure, and easier to change without editing the main compose file. Here's an example with a Postgres database. In the .n file, we define three variables: Postgres_user equals admin, Postgres_password equals secret, and Postgres_db equals mydb. Then in the docker-compose.yml file, we reference those variables inside the environment section. Notice the syntax: $curly brace variable name curly brace. For example, Postgres_user : $curly brace Postgres_user curly brace. When Docker Compose runs, it replaces that placeholder with the value from the .n file. The result: your Compose file stays clean and reusable. And you can easily switch configurations by editing only the .n file. Let's quickly summarize what we learned in Chapter 6. First, we saw why Compose exists. Instead of writing long and complicated Docker run commands, we can describe everything once in a docker-compose.yml file. Second, we learned that this file defines services such as a web app and a database, all in one place. Third, we practiced the most important commands. Docker-compose up starts everything. Docker-compose down stops and cleans up. And Docker-compose logs lets us see what's happening inside all services. Finally, we looked at the .env file. This is where we store secrets, usernames, passwords, and other configuration, so the Compose file stays clean and reusable. With these tools, you can now build and run multi-container applications with just one command. This is a big step toward working like real developers do in modern projects. Checking logs. Docker logs. When something goes wrong with a container, the very first place you should check is the logs. Docker captures everything the container writes to its standard output and standard error streams. You can see this output using the command docker logs followed by the container ID or name. If you want to watch the logs live as they update, add the -f option. Think of this like the tail command in Linux. You can also limit how much history you see with --tail followed by a number. For example, --tail 50 will show only the last 50 log lines. This is one of the most common and useful tools in real work because it helps you quickly understand errors, crashes, or startup issues. Here are some practical examples. First, Docker logs my-nginx shows all logs for a container named my-nginx. If you want to watch the logs in real time, type docker logs-f my-nginx. This is very useful for web servers like Nginx or databases like Postgres, where activity happens continuously. To avoid scrolling through too much history, you can limit the output. For example, docker logs-tail 20 my-nginx shows only the last 20 log lines. With these options, you can quickly find and follow exactly the logs you need. Monitoring. Docker stats. Docker top. Logs tell us what an application is saying, but sometimes we also need to know how it's performing. That's where monitoring commands come in. First, we use Docker stats. This shows a live table of CPU, memory, network, and disk usage for all running containers. It's similar to the Linux top command, but for containers. You'll use this when you want to check if a container is consuming too much memory or CPU. Second, we use Docker top, followed by the container ID or name. This shows the processes running inside that container, just like the top command on a Linux system. It's especially useful when a container is stuck or not responding, because you can see exactly what it's doing. Together, Docker stats and Docker top give you a quick health check on your containers. Here's how these commands look in action. If you type Docker stats, Docker will print a live table. For each running container, you'll see CPU percentage, memory usage, network activity, and block input and output. It updates continuously until you stop it with Ctrl+C. If you want to see what's happening inside a specific container, try docker top my-postgres. This will list all the processes currently running inside the Postgres container. With these two commands, you can quickly spot performance issues and debug containers that misbehave. Restart policies. In real projects, you don't want your containers to stay down if they crash or if the machine restarts. That's where restart policies come in. By default, Docker uses the no policy. That means the container will not restart automatically. If you set the policy to always, Docker will restart the container every time it stops, no matter the reason. With on-failure, Docker will only restart the container if it exits with an error code. This is helpful for services that should retry on crashes, but not on clean shutdowns. Another popular option is unless-stopped. This means Docker will always restart the container unless you stopped it yourself. You can configure restart policies with the --restart flag when running a container or in your docker-compose.yml file. This is a critical practice in production environments because it keeps your services running without manual intervention. Here's how to apply restart policies in practice. If you type docker run -d --name my-nginx --restart always nginx, Docker will run an nginx container in the background and restart it every time it stops. If you type docker run -d -name my-postgres -restart unless-stopped Postgres, Docker will keep the Postgres container running even after crashes or reboots, unless you manually stop it. With these settings, you can make sure your containers keep running automatically, which is essential for reliability in production. Cleanup. Over time, your system fills up with stopped containers, old images, dangling networks, and unused volumes. All of these take up disk space and can slow down your work. Docker gives us a cleanup command, docker system prune. When you run it, Docker will remove all unused containers, networks, images, and cache. By default, it will not remove unused volumes or all images. If you want to also remove unused images, add the option -a. If you want to also remove unused volumes, add --volumes. Be careful when using this command because the cleanup is permanent. Once deleted, those resources are gone for good. That said, this is a very useful command to keep your environment clean and avoid wasting space. Let's quickly review what we learned in Chapter 7. First, we used Docker logs to check what a container is saying. This helps us debug errors and crashes. Second, we looked at Docker stats for live CPU and memory usage, and Docker top to see the processes running inside a container. These commands are like health monitors for your containers. Third, we explored restart policies. With options like always or unless stopped, we can make sure containers automatically restart after a crash or reboot. Finally, we learned about Docker system prune. This powerful cleanup command removes unused containers, images, networks, and volumes, helping us save disk space. With these tools, you can troubleshoot problems and keep your Docker environment clean and reliable, skills that are absolutely essential in real jobs. Dockerize a simple web app. Now we move from learning commands to building something real. In this mini project, we will create a simple web application stack using Docker. The stack will include two main parts. First, a web app, built either with Node.js or Python Flask. Second, a database, such as Postgres or MySQL. We will use Docker Compose to define both services in one file, so they can talk to each other automatically. To make sure our database data is not lost, we will add a volume for persistence. At the end, you'll be able to run the entire project with a single command, just like in real development environments. This project will bring together everything we have learned so far and show you how Docker is used in real jobs. Dockerize the web app. We will start our project by creating a simple FastAPI web application and Dockerizing it. First, we write a Python script called main.py. This script creates a FastAPI app with just one route. When we open the web page, it will display the message, "Hello" from Docker and FastAPI. Second, we create a Docker file to build an image for the app. The Docker file will use the Python 3.9 Slim image, copy our application into the container, install FastAPI and Unicorn with pip, and run the app with Unicorn. The app will listen on port 8000, so we expose that port in the Docker file. With this, we will have a working FastAPI app running inside Docker. Here's how the code works. The main.py file imports FastAPI and creates an app instance. We define one route, /, which returns a JSON object with the message, "Hello" from Docker and FastAPI. That's all we need for a minimal FastAPI app. In the Docker file, we start from Python 3.9-slim as the base image. We set the working directory to /app and copy our Python file into it. We install FastAPI and Unicorn using pip. We expose port 8000 because that's where Unicorn will serve the app. Finally, the command Unicorn main:\app --host 0.0.0.0 port 8000 runs the application. When we build and run this image, our FastAPI app will be available on port 8000. Add database with Compose. Now that our FastAPI app is Dockerized, let's add a Postgres database using Docker Compose. The power of Compose is that we can define multiple services in one file. In our case, we'll define two services. First, the web service, which is our FastAPI app. Second, the DB service, which runs Postgres. Both services will automatically be connected to the same network created by Compose, so they can talk to each other by name. This means our FastAPI app can connect to Postgres using the hostname DB instead of an IP address. This setup looks very much like a real project, a web app with a connected database. Here's what the Compose file looks like. At the top, we set the version to 3.9. Then we define our first service, web. It is built from the current folder using the Docker file we created earlier. We map port 8000 on the host to port 8000 in the container, so we can access FastAPI in the browser. We also add depends _ on DB, which means the web app waits for the database container to start first. Next, we define the DB service, which uses the image Postgres:13. Inside the environment section, we set the username, password, and database name. Finally, we expose Postgres on port 5432, which is the default database port. With this Compose file, we can now start both the web app and the database together with one command. Notice the line depends _ on DB. This means the web container depends on the DB container. Docker Compose will start the database container first and then start the web app. This ensures that the FastAPI app doesn't try to connect to the database before the database is ready. It is also important to mention that for the port mapping, the first number is the port on your local machine, and the second number is the port inside the container. So 8000:8000 means traffic from port 8000 on your computer is forwarded to port 8000 inside the FastAPI container. Add persistence with volumes. One very important point for real projects is that containers are temporary. When a container stops or is removed, any data inside it is also deleted. This is a big problem if you're running a database like Postgres, because you don't want to lose all your tables and data every time you restart. To solve this, Docker provides volumes. A volume stores data outside the container in a safe location managed by Docker. Even if the container is deleted, the data inside the volume will still be there. In our project, we will add a volume for the Postgres database. This way, the database files are persistent, and we can restart the container as many times as we want without losing information. Now let's walk through the changes in the Docker Compose file. In the DB service, we added a new section called volumes. Inside it, we wrote -db_data:/var/lib/postgresql/data. This means create a volume named db_data and mount it to the path where Postgres stores its database files inside the container. That path is /var/lib/postgresql/data. At the bottom of the file, we also declared the volume with volumes, :db_data:. This is how Docker knows that db_data is a named volume. The result is, even if the DB container is removed or recreated, the actual database data is safe inside the volume. When you run Docker Compose up again, the database container will connect to the same stored data. This is how we make sure our database is persistent. Run everything with one command. Now that we have defined both the FastAPI app and the Postgres database in our Docker Compose file, we can start them together with just one command. Normally, without Compose, we would need to run long Docker run commands separately for each container, but with Docker Compose, we only need to type Docker Compose up. This command reads the Docker Compose file, creates the containers, sets up the network, and starts both services. It will also print the logs of both containers in the terminal, so you can see what is happening in real time. When you want to stop the containers, use Docker Compose down. This will stop and remove the containers, but the volume we created for the database will remain safe, so the data will still be there the next time you start. This is the real power of Docker Compose, running a complete stack with just a single command. Push and pull images with Docker Hub. Now that we have a working Docker image for our FastAPI app, the next step is deployment. In the real world, you often need to share your image with other team members or run it on another machine. Docker Hub is a cloud registry that stores images online. The workflow is simple. First, we tag our local image with a name that includes our Docker Hub username. Then, we push the image to Docker Hub. This uploads it so anyone with access can download it. On another machine, we can pull the image from Docker Hub using the docker pull command. Once pulled, we can run the container exactly like we did on the original machine. This process allows you to move your application anywhere without rebuilding it, which is essential in real projects. In this example, first, log in to Docker Hub with Docker Login. You will enter your Docker Hub username and password. Next, tag your local image. For example, Docker tag FastAPI-app, your username, /FastAPI-app:\latest. The tag tells Docker Hub who owns the image and which version it is. Then, push the image using Docker push your username, /FastAPI-app:\latest. Docker will upload the image layers to your account on Docker Hub. On another machine, you can download it with Docker pull your username /FastAPI-app:\latest. Finally, run it with Docker run -d-p8000:8000 your username /FastAPI-app:\latest. Now your FastAPI app is running exactly like it was on your original machine. This is the simplest way to share and deploy Docker images in real projects. Intro to multi-stage builds. In development, Docker images often contain extra files and dependencies we don't need in production. These extra files make images bigger and slower to download. Multi-stage builds solve this problem. With a multi-stage build, you can have multiple from statements in the same Docker file. The first stage is usually the build stage, where you install all dependencies, run tests, or compile your code. The second stage is the production stage, where you copy only the necessary files from the build stage into a smaller, clean base image. The result is a smaller, production-ready image, which is faster to deploy and easier to manage. Let's explain this example step by step. The first stage is called Builder. We start from Python 3.9-slim, set the working directory, copy our app, and install dependencies. The second stage is the production stage. We again start from Python 3.9-slim, which is a clean image without unnecessary build files. We copy only the contents of the build stage using copy --from equals builder/app/app. Finally, we expose port 8000 and start the app with Unicorn. Using this approach, the production image contains only what is necessary to run the app, making it much smaller and faster to deploy. Security basics in Docker. Security is a critical part of deploying Docker containers in production. First, never run your containers as root unless absolutely necessary. Running as root increases the risk of privilege escalation if an attacker gains access. Instead, create a non-root user in your Docker file and switch to it before starting the app. For example, using the user instruction in Docker file. Second, prefer lightweight base images, such as Alpine Linux. Alpine images are smaller, with fewer packages, which reduces the potential attack surface. Finally, keep your images minimal and regularly update both the base image and dependencies. This ensures you have the latest security patches and reduces vulnerabilities. By following these simple rules, you make your Docker containers safer for production use. In this example, we are building a safe and small Docker image for our FastAPI app. First, we start with Alpine Linux as the base image. Alpine is a very small and lightweight Linux distribution. Using Alpine makes the image smaller, faster to download, and reduces security risks. Next, we create a new user inside the container called myuser. We use the command run adduser-d myuser. Here, run executes commands during image build. The adduser command adds a new user, and the -d flag means create with default settings without a password. This user will be used instead of root, which is important for security. Then, we set the working directory with workdir/app and copy the FastAPI app into the container. We also install dependencies with run pip install FastAPI Unicorn. After that, we switch to the non-root user using user myuser. This ensures that the application and all subsequent commands run as myuser, not root. Running as a non-root user is a security best practice in production. Finally, we expose port 8000 and start the FastAPI server with Unicorn. With this setup, the container is small, safe, and production ready.
Thanks for watching.